Okay, so maybe I'll offer some remarks here. So I think what you're highlighting is the desire. So this question is highlighting the desire to capture infection spread, contagion processes. But it's really, in my mind, a question about scope. What needs to be endogenous in a system? Um, how much detail is really needed in terms of the processes of the system? To what degree is there a need to represent mobility processes to capture the contagion, or to what degree we could approximate that with things like degree distributions in a static network, where those degree distributions are informed by contexts that might in fact take place at physically distributed locations, but they're boiled down to a static network which connects, say, animals to other animals or what have you. So the fact that this animal moved amongst several locations, you might say, well, that induces a contact network effectively that we use to summarize their contacts, and we gloss over, we abstract away from exactly where are those contacts taking place at what time during the day, on what days, and we treat it as essentially mixing across a contact network. So that is sometimes done. And I would particularly highlight some of the work that Wade has done in pertussis modeling, together with colleagues. Postdoc co-led by myself, Karsten Hempel, who's now at the Institute for Health Economics in Alberta, and Alex Doroshenko being the lead PI on the project with Alberta Health Services and University of Alberta. And this model was actually one we were thinking of having a case study on it. And what it in fact does is in a way kind of a nice application of what the idea you put forward there, sort of summarizing effects of much mobility with a static network. What it does is it has, for example, schools, homes, but it doesn't actually simulate like mobility of an individual among them. It's sort of a weighted network whereby a certain amount of the contacts occurring are school contacts, and have a certain weight, as I recall, associated with them. Other contacts are home contexts, and those have other weights. And so rather than saying like, okay, all the kids are together in the school for this period of time and now they're home, all the kids are home or at school or home, we just are turning that into a network and then simulating the spread of pertussis in this case over that network. And we've done this in quite a few other papers as well, including with data gathered from real world mobility, like mobile populations and mobility networks with empirical mobility, like traveling people around, having contact patterns, and then boiling that down, like simulating that on the actual contact patterns and contrasting it with what we find through a simulation on the static network, which is induced by that, or the time, or a network which updates only occasionally. And uh, and so what we found is basically for certain ranges of infection types and certain types of characteristics of infection based on the characteristic of infection. We did this for kind of simulations with maybe 15 different infection types, spanning the gamut from viral infections to mycobacterium tuberculosis with long latent times to to a couple of types of COVID, variants of COVID, et cetera. And the static network does diverge from the mobility, simulating it with the mobility patterns directly for certain infections and basically certain types of needs with it. I would suggest, by the principles of starting simpler, you're going to want to err on the side of using a weighted network for this, but you need to reflect. So the motivations for making things endogenous in a model, I tend to group them into a couple sorts. And this has offered some students value in the past. So I'm going to, at the cost of calling up some slides here, I'm just going to try to draw out some a few principles associated with why we represent things endogenously, and factors. Yes, here we go. Okay, these slides I think I have posted, but I will show them here and discuss a little bit. So here we go. And I'll also refer you to our paper if you'd like to see this. But it's a fairly it glosses away from the key question in my mind, was what are you trying to get at? Like what's your measure that you're trying to get out? If it's cumulative infections, over time, it may be that a mobility, like a static network, might be pretty good. But if you're trying to investigate certain interventions, sometimes those are much easier simulated within a mobile context. So a key question I ask is, like, are there certain interventions you want to characterize that will actually be much easier to characterize one way or the other? For example, with a static network, with weights, would that afford you an elegant way of capturing certain interventions? Or do those interventions, I'm thinking about something like hosing down vehicles for transporting cattle or transporting pigs, or disinfectants for poultry barns, or types of testing regimens that are occurring within at certain points in the mobility process. If there are certain things that occur during mobility or because of mobility, like there's a truck and it is used to transport, and then we hose it down more for this intervention, we clean it off more. If we want to simulate that might be hard to kind of post fit into a static network representation. And so you're going to want to think about the interventions at issue. And are those interventions things that require an extra level of detail? There are times where, you can just use a static network, and there are times you want extra detail because it's needed to to simulate the intervention in a meaningful way. For example, if I'm dealing with HIV/AIDS, like maybe it's fine to, for my purposes, to simulate a static network of contact between people that glosses over, maybe I distinguish sexual contact for needle sharing contact for intravenous drug use, but other than that, I gloss over the context and so on. But if I want to simulate the effects of needle sharing, um, uh, and the degree to which provision of clean needles would could help lower transmission, it's going to be much easier to characterize that if you're simulating kind of people, a set of people coming together who would otherwise share needles, and then go across, because that's not something at one point in the network. It sort of is going to affect different people at different points in their networks. And in as much as you have a shared place where people come together to share needles, like that might be a place that sort of intervention would really be helpful. Or if you're going to simulate a supervised consumption site or something for harm reduction, that might benefit from a mobility type characterization. So you want to think about the interventions, and you want to think hard and talk with someone with some experience in modeling. And I would suggest talk with TAs here to brainstorm a bit about this. Like for my interventions, could I capture it with a simpler representation? If so, in general, I'd say go with a simpler representation. But if there are certain things where you're getting stuck and it seems like you need the more detailed representation, you want to give that due attention. And maybe you want to say, okay, first we'll make the simple one. We'll learn from that. And then we'll tentatively plan to go on to a more detailed one to look at these other interventions if we still have that as a priority. I would always start simple. Again, don't try to build the bigger, better model. Don't make great the enemy of good. Start with the good, and what your conception is of the great will come as you learn. Is there data available to inform, or theory available, guiding theory to inform an understanding of these transport processes? If not, if that would involve a lot of speculation, then it's often better to just say, okay, for this model, we'll use a scope which doesn't try to probe at that level where theory or understanding quantitatively is not available for what's going on. We will summarize it with a contact network that is a weighted contact network. Another aspect is if there's an issue of heterogeneity that comes up in the context of the actual mobility process, that is hard to capture with a static network, like certain measures that take place that help guard against infection transmission in certain ways of the mobility process. You're going to want to think about that as well. I sometimes use these in addition to those comments. Why would you try to characterize it in a model versus ignore it? Well, one thing you want to bear in mind is if you genuinely believe that from what you're hearing, from what you know about what's going on, that you really can't adequately capture the process without attending for this. If it's all about, contamination on transport vehicles, or something about the particular ways in which animals are sorted when being brought to a feedlot from a cow-calf operation, then you you might really want to think about capturing that process, because that might be at the heart of where you can intervene, but also at characterizing what's going on. It might be the place where you could test. It might be a place where data could be collected, and so you want to think about characterizing it. But if it's a key mediator for the process, if you have to capture the effect of an intervention, that was this notion. Or you really want to capture how it will be affected by an intervention. Like, you want outcome measures. You want it in your model. If you want to know something about how, harm reduction in the form of a supervised consumption site will lower HIV/AIDS deaths, deaths from HIV/AIDS, then you're going to need a model that includes mortality. Very likely. Right. Or if you're concerned that certain effects will have disproportionate favoring of certain subgroups, you might want to consider that in your model. If there's something that's observable in the world, and to relate it to something in the model, you need a corresponding thing in the model to be able to ground the model in observations. You have observations about XYZ from the population, and you want a model where you can have kind of a simulated XYZ that can be compared to those things in the world to cross-check the model, challenge it, make sure you're not way off base. And so if there's something in the world that's observable, and you can have a corresponding thing in the model with a modest amount of work, often that's something you want to do, because it lets you pin the model down in terms of empirical observations for that thing, bring expertise to the table. And finally, and again, the last component on each of these slides is, if something's very important for stakeholder credibility, if you need to be able to point to something and talk about things at that level to convince someone that it's worth sharing data with you or listening to you, I think often that's pretty important, and you want to take that into account when thinking about the evolution of your model scope. But for all of these cases, it's always start small, start with simple, build from there, learn. This just gives you maybe a sense of where things might need to go. And what you don't want to do is plan around something that you are very confident will be unable to carry over for some of these needs, like where you're going to be unable to look at the interventions of the issue because the model's at a level that it just doesn't allow those interventions, the effects of them, to be expressed in ways people care about, or them to be simulated in a way that will carry through to those effects. I don't know if those are helpful. I feel I haven't really done it justice, but those are some thoughts, and I would talk with the TAs. I particularly highlight Wade's experience with boiling down from mobility networks to static networks. This is something that was done in the COVID context, where we had long-term care facilities. We had workplaces, we had homes, etc., but we didn't have mobility in it. And it was done with the pertussis models as well. So I would talk with the TAs. Hopefully those comments are helpful.
Thank you. That's really super insightful. And yeah, it's exactly like you're saying. I think I also started adding too much complexity before I even started testing like the within spreads. But it is like with especially animal networks, we deal with like scale-free networks. So I have I
Yeah.
do have static networks, but it's daily. So I have at the daily level.
Oh yeah.
And I have that data. So I would like to use that to target like high centrality nodes and put interventions
Yep.
on specific nodes.
Ye-
But yeah, I would appreciate if you could share the papers, I don't know, later today or something with
Sure. Sure.
on the
Yeah.
chat or something. And yeah,
Absolutely.
if there's availability to like talk with one of the TAs, I would also love. I can send an email later. And I would love to brainstorm as well. Thank you.
Absolutely. Yeah, and I'd encourage other participants to do the same. Please take advantage of this wealth of expertise that is represented in the TAs. Uh, since you mentioned scale-free networks, um, I will note a couple things. I mean, um, yeah, number one, um, uh, AnyLogic has a set of about 5 or 6 built-in network types. What's sometimes called Erdos random or Poisson random or Bernoulli random networks, which are two people are connected in a network with a certain probability. It has small world networks, which are a combination of that uh, and a ring lattice network. It has ring lattice, which is extremely uh, extremely localized. Um, it has scale-free networks and it has distance-based networks, which we saw yesterday. Um, uh, those networks are represented at a very basic level. If you, we've done a lot of work with AnyLogic models, building our own network structures, and Wade again knows a lot about this. My now graduated student Winchell Chen, who is behind that paper, which used mobility data from smartphones, and compared, you know, fully static networks to networks where the characteristics of a network change up to even every 5 minutes in frequency and in between, and looked at how that granularity of of detail in the network um, affected the effects of simulation over that network and like cumulative infection count or what have you. Um, he um, he did a lot of work putting networks into AnyLogic as well. You can put scale-free networks in AnyLogic, and I think some of them, maybe one of the models I've provided, may even have the construction uh, of a scale-free network as part of that model. There are a couple models which build up networks manually um, with, for example, certain heterogeneity or certain preferential mixing pattern associated with it. Um, the issue here is not whether you can do it; it's what's the most elegant way to do it, and what's a means that won't overwhelm you by the sort of software engineering of it. But it's very readily done. Building up network structures if you're inclined to do that, and imposing time varying networks like that might vary by the day. That's also very readily done. I would say if you have something approaching a network, a scale-free network on a daily basis, I would say that's very impressive. And I would say, representing mobility beyond that, um, in terms of infection spread, like for a given configuration, it may not be that it yields all that much more accuracy. The real question in my mind would be, about the interventions. Like, are the interventions such that they need to talk about the mobility agents again, like I said, the trucks or the holding pens when shifting animals, or the disinfection procedure when moving animals between areas, or what have you. And I would um, I would think about that. Yeah, but enough said. Hopefully those comments are helpful.